Hello everyone, I'm Subarna. I'm a postdoc at the Data Systems Lab at Harvard, and today I'll be presenting the paper Cosine, a cloud cost optimized self-designing key-value storage engine. This is a joint work with Meena, Wilson, and my advisor Stratos. Now, to begin with, storage has always been a critical part of systems because they simply control how data is read and written into a system. And this is becoming more and more important now because we are building super complex data systems. So how much performance we can actually extract from a system largely depends on the efficiency of the underlying storage solution. Now, we are living in a fascinating time where everything around us is changing too fast. So, for instance, data is growing at an exponential rate, both in terms of volume and velocity. We are seeing super exciting hardware trends with persistent memory, FPGAs, GPUs, and TPUs. Applications are getting more and more diverse almost every single day. And even our performance goals have expanded a lot. So basically, the context with which data systems are built is continuously changing. And as data system designers, we have to keep up with this change. Now, today, of course, we cannot build a new data system for every single context because designing data systems is complex and this is something that cannot be done overnight. So what we do instead is that we take existing systems and we make them adapt to this new environment. And this somehow locks us into suboptimal data system designs, some of the immediate side effects of which are high cloud cost or low performance or high energy consumption, high cost of transitioning, and so on. Now, the source of the problem is the inherent complexity in the design process of data systems because there are way too many factors and metrics that affect cloud cost and performance. So for instance, as a data system designer, if I want to run my own application on cloud, then I will have to start off by making several decisions. So the first decision is, who would be the cloud provider for my application? And this itself is a tough choice because there are so many providers out in the market and each of them has their own unique pricing policy and hardware offering. So the next decision I'll have to take is, what would be the storage engine design for my application? Now, at the core of storage engines are data structures and algorithms that control what kind of performance the engine will optimize for. So for instance, if it's a B-tree-based storage engine, this will optimize more of reads. Whereas if it's a log-structured merge-based storage engine, this will optimize more of writes. And in addition to these popular choices, there are so many other designs that are there in this space, which could be either tunings of existing designs, or they could be hybrid designs, or completely new designs with different performance properties. Now, thirdly, while you may think that, well, storage engines and cloud provider and hardware are their own decision spaces, but we actually cannot take any decision about them in isolation because the overall performance that we get is a function of the holistic combination of the storage engine designs, hardware, and the cloud provider. So any decision we take really maps to this performance space. And not to forget that workloads, of course, are getting more and more complex with different types and proportion of operations. So then this becomes an exhaustive decision space. And the problem really stands in the fact that firstly, the space is pretty complex. Like you can see, there are so many layers and interrelationships. This is a vast space where the cardinality of all possible combinations can quickly reach up to sextillions, which is in the order of 10 to the 35. And today, most of our decision about each of these layers is manual, which is only likely to be suboptimal given that the space is so vast and complex. Now, given this is the problem, an ideal or dream solution here would be that if for every application context, we can create the perfect storage engine solution so that the design of the storage solution is specifically tailored to the task at hand. And that is basically the goal we are aiming for. Now, before we jump into the solution, here's our take on how we approach the problem. So our key intuition is that there is really a massive space of all possible storage engine designs. And we can think of every storage engine as a set of low-level decisions or fundamental principles. So each of these points here is a unique storage engine design. And all existing storage engines that we have out there today comprise a very small set of this massive space of possibilities. And we are asking ourselves this question, that what if we can reason about this massive design space? Now, by reasoning, we mean two things. So firstly, being able to correctly identify what are these design principles that participate in the process of designing storage engines, and how each of these principles actually affect cloud cost and performance. If we are able to do both of these, then given any context, let's say a workload and a budget, we will be able to navigate through this space and find out that perfect storage engine solution that maximizes the performance goals of that input. Now, towards this, we propose Cosine. Cosine is a self-designing storage engine that takes in a workload and a budget as input, and it navigates through this whole space of storage engines and comes up with a storage engine configuration that optimizes the cost performance trade-off for that input. And by configuration, here we mean the storage engine design, the hardware on which the design will be deployed, and the cloud provider for the hardware. Now, we'll first start off with the workflow and high-level architecture of Cosine. Now, at its core, Cosine contains a storage engine template. Now, this is a dictionary of design abstractions that allow us to create structured descriptions of arbitrary key value storage engines that fall in the space. So this has two parts. So firstly, layout primitives that contain design choices about how data can be stored. And then there are algorithmic abstraction that contain choices about how the data can be accessed. Now, just to exemplify a little bit more, if we zoom into the layout primitives, there are several design questions associated when we think of designing a data layout. So for instance, how much of data goes to memory, how much goes to disk, within disk if we are storing as flat logs or maybe hierarchical format like trees, how do these trees grow, even within memory, how do we allocate memory across buffers or auxiliary data structures like filters and indexes and so on. Now, each of these questions has multiple answers, and by taking each of these design choices together, Cosine creates a superstructure that encapsulates all possible storage engine designs that fall in this space. So now, by setting different values to each of these design primitives, we can start synthesizing not only classical layouts like a leveled LSM tree or a B tree or tiered LSM tree, but we can also create new hybrid layouts. For instance, we can have like an LSM-like structure on top for hot levels and a B tree-like structure for the cold levels. And similar to the layout primitives, Cosine also has algorithmic abstractions. And by setting different values to now both layout and algorithm, Cosine's storage engine template can now start spanning across trillions of storage engine designs that not just include an existing design like RocksDB, WireTiger, or Faster, but now it can include new storage engine designs as well. Now, next, Cosine contains cost models to evaluate each of these template specifications. And I'm going to talk more about this in the subsequent slide, but at a high level, these models take into account the cost incurred within storage engine for data movement, CPU effects, and hardware parallelism. And once we have the means to evaluate templates, then Cosine contains a search algorithm that navigates through the whole space. It prunes out suboptimal designs and eventually creates a cost performance continuum, which is a Pareto frontier mapping several cloud costs to performance. And for each of these points, Cosine also keeps a track of the optimal configuration that's responsible for that performance. And once we figure out the optimal configuration for the input budget, then Cosine performs its last step where it materializes the actual code for that configuration. So for that, Cosine contains a templated key value storage engine in Rust that containerizes all the basic functionalities of a storage engine for reading and writing data, for doing garbage collection, capacity checks, and so on. So based on the template specification, Cosine would activate or deactivate different parts of the code and eventually generate the code ready to be used by the input workload. Now, so these are basically the four different modules of Cosine, where each of them has their own functionalities, their opportunities and challenges. But for the sake of time, for the rest of the talk today, I'll be focusing on the cost model part of Cosine. Now, the cost model takes in a template specification, a hardware and a workload as input, and it comes up with the expected latency of running the workload on the storage engine as specified by the template. And this model is actually invoked once for each of the storage engines that fall in the overall design space of Cosine. So that now not only we can evaluate every template specification, but we can also compare and rank between several designs. And then all of this actually becomes a part of Cosine's search algorithm that runs on top, that actually navigates through the whole space and comes up with the optimal storage configuration for the set of inputs. And this is basically how the model actually fits in the overall pipeline of Cosine. Now, to zoom into the model intrinsics, the model takes into account two dominant cost factors that are consequential to performance. So the first one is IOs for reading data to and from the disk. And the second is the effect of concurrency that takes into account how much of this data movement can be actually accelerated through parallelization because of the number of available hardware cores. Now, our key intuition for model design is to think about, is to decouple the concurrency and IO logic and think about concurrency as a separate layer that adds, that augments speed up on top of an underlying single threaded system. And this actually allows us to do a modular analysis and reasoning about functionally different parts of hardware like CPU and storage, but at the same time, it allows us to take into account their collaborative impact on performance. Also, to make the model both fast and accurate, we actually bring in both analytical and learned components as part of the model design so that they can coexist and feed off each other to actually make our latency predictions more accurate. So for instance, the IO model is an analytical model that comes up with latency estimate coming from IOs. And then the concurrency model that works on top of the IO model is a learned model that actually discounts some of these time due to available hardware cores. Now, to quickly look at the inside of these models, the first step of the IO model is the design morphology step, where the model reads the template and tries to estimate or understand the high-level data structure class of the design, if it's a B tree or an LSM tree or an LSH table. So, for instance, if the growth factor is in the multiples of block size, or if there is no Bloom filter, or the number of runs per level is 1, then the model infers that this is more of a B tree class of design. And in the second step, once it knows what is the high level class, and the model tries to understand the exact shape and size of the design. So for instance, by looking at the distribution of data and the workload, the model can figure out if it's a fat tree or a deep tree, or how many levels are there in the tree, the capacity of level, and so on. The second step is basically to leverage the structure it has obtained in step 1 and come up with an estimate of the IO cost of each fundamental key value operations like lookups, inserts, updates, and range queries. So for instance, for lookups, the model will actually reason about the probabilistic existence of keys at different levels of the tree, and it will infer if for a lookup, a query always has to go to the end of the last level of the tree like it happens in a B tree, or can it terminate early as well as it happens in an LSM tree. And once the model comes up with the per operation IO cost, then it performs the last step where it actually generates the latency coming purely out of IOs for all the operations in the workflow. And that is the first starting point for the concurrency model. Now, the concurrency model is based on Amdahl's law that gives up the theoretical speed up a workload can attain when it's fed with a certain number of cores. So the central idea is that every program has a sequential part and a parallelizable part. And as we add more cores to the program, it's only the runtime of the parallelizable part that reduces. So for Amdahl's law to be worked on cosine, we need to know the proportion of parallelizable component in cosine, or the value of f. Now remember that cosine is not a single design, but it can span across trillions of possibilities. But we observe that f shares similar values for designs that share the core fundamental principles. And so we can only learn the value of f for drastically distinct design classes. So what we do is that we decompose the entire design space into 5 different distinct design classes. And for every key value operation, we learn the value of f. So for each combination of an operation and a design class, f is learned as an aggregate of several benchmarking trials by varying the hardware specification, the number of operations, the base data, and the degrees of parallelism. And once we know the value of f, for each operation design combination, we can also get it for the whole workload based on a weighted average, based on the workload's proportion of operations. Okay, so now that we have learned some of the inside of the models, and we know that the modeler is a key enabler of Cosine's actual search algorithm that enables Cosine to pick the optimal configuration, we'll now see how Cosine eventually uses these to self-design itself for the problem at hand. So here's a YCSB-E variant workload where we show different cloud budgets along the x-axis, and we are going to show the throughput of different systems and cosine along the y-axis. So we start off with existing baselines, WireTiger, RocksDB, and Faster. For each of these systems, at every budget point, we procure as much resources we can for that point and record the performance by deploying the default configuration of the system. And parallelly, we let Cosine search across the massive space of design for every budget point and record its performance. Now, we observe that firstly, Cosine offers up to 2 orders of magnitude performance higher than that of existing storage engine designs, but also every configuration along every budget point is unique. So for instance, if we just sample 3 different points along Cosine's curve, we'll see that the first one is a B-tree-based storage engine configuration running on Azure using up 64 gigs of memory. The second is a leveled LSM-based storage engine running on Amazon using up 128 gigs of memory, whereas the third is a completely different design. It's a hybrid design having LSMs on top and B-trees on bottom. It's running on GCP using 128 gigs of memory. And even 2 or more designs falling in the same design class can actually have very different tunings. So for instance, for 2 hybrid designs, you will notice that the exact tuning of the size ratio, the merge thresholds, the total memory allocation, the degrees of parallelism are all very, very different. So basically, a full-fledged cosine curve looks like this, where we have several cloud providers and design classes along different cloud budgets. And we repeat this experiment for 10 different workloads across and beyond YCSB. And for each case, we see that cosine either matches or outperforms existing storage engines. Now, as we conclude, we'd like to say that Cosine is an ongoing effort in the direction of instance optimized systems. And currently, there are several ongoing research directions that we're working on that includes extending Cosine for adding new data structures, algorithms, cloud providers, and hardware, but also adding new functionalities to Cosine like robustness or adaptability. Thank you for listening.